This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Kelly Bescher of Mattapoisett, Massachusetts. Relativity, the Special and General Theory, by Albert Einstein. Part 1, The Special Theory of Relativity. Sections 1 through 3. Section 1. Physical meaning of geometrical propositions. In your school days, most of you who read this book made acquaintance with the noble building of Euclid's geometry, and you remember, perhaps with more respect than love, the magnificent structure on the lofty staircase of which you were chased about for uncounted hours by conscientious teachers. By reason of our past experience, you would certainly regard everyone with disdain who should pronounce even the most out-of-the-way proposition of this science to be untrue. But perhaps this feeling of proud certainty would leave you immediately if someone were to ask you, "What, then, do you mean by the assertion that these propositions are true?" Let us proceed to give this question a little consideration. Geometry sets out from certain conceptions such as plane, point, and straight line with which we are able to associate more or less definite ideas, and from certain simple propositions or axioms which, in virtue of these ideas, we are inclined to accept as true. Then, on the basis of a logical process, the justification of which we feel ourselves compelled to admit, all remaining propositions are shown to follow from those axioms, i.e., they are proven. A proposition is then correct or true when it has been derived in the recognized manner from the axioms. The question of truth of the individual geometrical propositions is thus reduced to one of the truth of the axioms. Now it has long been known that the last question is not only unanswerable by the methods of geometry, but that it is in itself entirely without meaning. We cannot ask whether it is true that only one straight line goes through 2 points. We can only say that Euclidean geometry deals with things called straight lines, to each of which is ascribed the property of being uniquely determined by 2 points situated on it. The concept true does not tally with the assertions of pure geometry, because by the word true we are eventually in the habit of designating always the correspondence with a real object. Geometry, however, is not concerned with the relation of the ideas involved in it to objects of experience, but only with the logical connection of these ideas among themselves. It is not difficult to understand why, in spite of this, we feel constrained to call the propositions of geometry true. Geometrical ideas correspond to more or less exact objects in nature, and these last are undoubtedly the exclusive cause of the genesis of those ideas. Geometry ought to refrain from such a course in order to give its structure the largest possible logical unity. The practice, for example, of seeing in a distance 2 marked points on a practically rigid body is something which is lodged deeply in our habit of thought. We are accustomed further to regard 3 points as being situated on a straight line, if their apparent positions can be made to coincide for observation with one eye, under suitable choice of our place of observation. If, in pursuance of our habit of thought, we now supplement the propositions of Euclidean geometry by the single proposition that 2 points on a practically rigid body always correspond to the same distance, line interval, independently of any changes in position to which we may subject the body, the propositions of Euclidean geometry then resolve themselves into propositions on the possible relative position of practically rigid bodies. Begin footnote. It follows that a natural object is associated also with a straight line. 3 points, A, B, and C, on a rigid body, thus lie in a straight line when the points A and C being given, B is chosen such that the sum of the distances AB and BC is as short as possible. This incomplete suggestion will suffice for the present purpose. End of footnote. Geometry, which has been supplemented in this way, is then to be treated as a branch of physics. We can now legitimately ask as to the truth of geometrical propositions interpreted in this way, since we are justified in asking whether these propositions are satisfied for those real things we have associated with the geometrical ideas. In less exact terms, we can express this by saying that by the truth of a geometrical proposition in this sense, we understand its validity for a construction with ruler and compasses. Of course, the conviction of the truth of geometrical propositions in this sense is founded exclusively on rather incomplete experience. For the present, we shall assume the truth of the geometrical propositions. Then, at a later stage, in the general theory of relativity, we shall see that this truth is limited, and we shall consider the extent of its limitation. End of Section 1. Section 2. The system of coordinates. On the basis of the physical interpretation of distance which has been indicated, we are also in a position to establish the distance between 2 points on a rigid body by means of measurements. For this purpose we require a distance, rod S, which is to be used once and for all, and which we employ as a standard measure. If now A and B are 2 points on a rigid body, we can construct the line joining them according to the rules of geometry. Then, starting from A, we can mark off the distance S time after time until we reach B. The number of these operations required is the numerical measure of the distance AB. This is the basis of all measurement of length. Begin footnote. Here we have assumed that there is nothing left over, i.e. that the measurement gives a whole number. This difficulty is got over by the use of divided measuring rods, the introduction of which does not demand any fundamentally new method. End footnote. Every description of the scene of an event or of the position of an object in space is based on the specification of the point on a rigid body of reference, with which that event or object coincides. This applies not only to scientific description, but also to everyday life. If I analyze the place specification, Times Square, New York, begin footnote, Einstein used Potsdamer Platz, Berlin in the original text. In the authorized translation, this was supplemented with Trafalgar Square, London. We have changed this to Times Square, New York, as this is the most well-known identifiable location to English speakers in the present day. Note by the janitor. End footnote. I arrive at the following result. The Earth is the rigid body to which the specification of place refers. Times Square, New York is a well-defined point to which a name has been assigned and with which the event coincides in space. Begin footnote. It is not necessary here to investigate further the significance of the expression coincidence in space. This conception is sufficiently obvious to ensure that the differences of opinion are scarcely likely to arise as to its applicability in practice. End footnote. This primitive method of place specification deals only with places on the surface of rigid bodies, and is dependent on the existence of points on the surface which are distinguishable from each other. But we can free ourselves from both of these limitations without altering the nature of our specification of position. If, for instance, a cloud is hovering over Times Square, then we can determine its position relative to the surface of the earth by erecting a pole perpendicularly on the square so that it reaches the cloud. The length of the pole, measured with the standard measuring rod, combined with the specification of the position of the foot of the pole, supplies us with a complete place specification. On the basis of this illustration, we are able to see the manner in which a refinement of the conception of position has been developed. A. We imagine the rigid body, to which the place specification is referred, supplemented in such a manner that the object whose position we require is completed by the completed rigid body. B. In locating the position of the object, we make use of a number, here the length of the pole measured with the measuring rod, instead of designated points of reference. C. We speak of the height of the cloud, even when the pole which reaches the cloud has not been erected. By means of optical observations of the cloud from different positions on the ground, and taking into account the properties of the propagation of light, we determine the length of the pole we should have required in order to reach the cloud. From this consideration, we see that it will be advantageous if, in the description of position, it should be possible by means of numerical measure to make ourselves independent of the existence of marked positions, those possessing names, on the rigid body of reference. In the physics of measurement, this is attained by the application of the Cartesian system of coordinates. This consists of 3 plane surfaces perpendicular to each other and rigidly attached to a rigid body. Referred to a system of coordinates, the scene of any event will be determined for the main part by the specification of the lengths of the three perpendiculars or coordinates, x, y, z, which can be dropped from the scene of the event to those three plane surfaces. The lengths of these three perpendiculars can be determined by a series of manipulations with rigid measuring rods performed according to the rules and methods laid down by Euclidean geometry. In practice, the rigid surfaces which constitute the system of coordinates are generally not available. Furthermore, the magnitudes of the coordinates are not actually determined by the constructions with rigid rods, but by indirect means. If the result of physics and astronomy are to maintain their clearness, the physical meaning of specifications of position must always be sought in accordance with the above considerations. Begin footnote. A refinement and modification of these views does not become necessary until we come to deal with the general theory of relativity, treated in the second part of this book. End footnote. We thus obtain the following result. Every description of events in space involves the use of a rigid body to which such events have to be referred. The resulting relationship takes for granted that the laws of Euclidean geometry hold for distances, the distance being represented physically by means of the convention of two marks on a rigid body. End of Section 2. Section 3. Space and Time in Classical Mechanics. The purpose of mechanics is to describe how bodies change their position in space with time. I should load my conscience with grave sins against the sacred spirit of lucidity were I to formulate the aims of mechanics in this way, without serious reflection and detailed explanations. Let us proceed to disclose these sins. It is not clear what is to be understood here by position in space. I stand at the window of a railway carriage which is travelling uniformly, and drop a stone on the embankment without throwing it. Then, disregarding the influence of the air resistance, I see the stone descend in a straight line. A pedestrian who observes the misdeed from the footpath notices that the stone falls to earth in a parabolic curve. I now ask, do the positions traversed by the stone lie in reality on a straight line or on a parabola? Moreover, what is meant here by motion in space? From the consideration of the previous section, the answer is self-evident. In the first place, we entirely shun the vague word space, of which we must honestly acknowledge we cannot form the slightest conception, and we replace it by motion relative to a practically rigid body of reference. The positions relative to the body of reference, railway carriage or embankment, have already been defined in detail in the preceding section. If instead of body of reference we insert system of coordinates, which is a useful idea for mathematical description, we are in a position to say, the stone traverses a straight line relative to a system of coordinates rigidly attached to the carriage, but relative to a system of coordinates rigidly attached to the ground, embankment, it describes a parabola. With the aid of this example, it is clearly seen that there is no such thing as an independently existing trajectory, literally path curve. Begin footnote. That is, a curve along which the body moves. End footnote. But only a trajectory relative to a particular body of reference. In order to have a complete description of the motion, we must specify how the body alters its position with time, i.e., for every point on the trajectory it must be stated at what time the body is situated there. These data must be supplemented by such a definition of time that, in virtue of this definition, these time values can be regarded essentially as magnitudes, results of measurements, capable of observation. If we take our stand on the ground of classical mechanics, we can satisfy this requirement for our illustration in the following manner. We imagine two clocks of identical construction. The man at the railway carriage window is holding one of them, and the man on the footpath the other. Each of the observers determines the position on his own reference body occupied by the stone at each tick of the clock he is holding in his hand. In this connection, we have not taken account of the inaccuracy involved by the finiteness of the velocity of propagation of light. With this, and with a second difficulty prevailing here, we shall have to deal in detail later. End of Section 3.